Let's look into the internals of latent diffusion model. As discussed earlier, latent diffusion model takes two input. One is the base image. So as discussed previously, latent diffusion model takes two inputs. One is the base image and the other one is the prompt as an input. And the latent diffusion models generates an image which is closer to the base image and the text conditions as specified in the prompt. So internally, a deep diffusion model is nothing but a deep neural network with several layers inside, and it has an input layer and output layer along with the several hidden layers, right? And that uses several operations like fully connected layers, perceptrons, then the linear activation functions, and it has the weights and the biases that are learned during the training process to generate this image. So it takes a noisy image as an input and it learns to create the clean image from this particular noisy image. And in the process, once the model is trained, it can generate a completely new image from the noise itself. So going a little bit into deep, actually the diffusion model doesn't directly work on the image. It works something on the latents, which makes it really fast. So latents are nothing but a lower dimensional representation of an image. So here is a noisy image as an input. We pass it through something called auto encoder. So the job of the encoder is to generate a lower dimensional representation of these latents, which are then processed by the diffusion model to remove the noise from the image. And again, the diffusion model outputs another set of latents, which are passed through another network called decoder, and the decoder is what generates the clean image. Okay, so the diffusion model only works on the latents, input as well as output. That is one important point I wanted to address here. So let's look a little bit more inside the different components of the diffusion model. So we already learned about this encoder, which is also known as a variational encoder, which converts this image into latents, which are then fed into the model, also called the unit, and the output of the model is again latents, which are again fed to the decoder to generate the clean image, right? And then main model that does the extraction of noise from the image is called the unit. Then another section is called the clip, also known as the contrastive language image pre-training. The job of this particular model is to convert the prompt, which is here, into something called embeddings, which is then fed to the variational autoencoder. So the encoder takes the image as well as this text embedding as an input, and then it generates the latents for both of them at the same time. Then the unit actually is the main module. It's again a deep neural network. That is the one that takes in latents as an input, and it generates the noise and separates the noise from the image and generates the clean image. Now the noise scheduler is another component. The job of the noise scheduler is to add a different level of noise to this particular image at different intervals, and trains the model in such a way that even if a variation amount of noise gets added, the model is robust enough to isolate the image from the noise. So a little bit deeper look into the unit. So unit consists of two components, the downsampler component, which is here, also known as encoder, and the upsampler component, which is also known as the decoder. Okay. So the job of the encoder is basically downsamples the image using the fully convolutional network. So as you know, the convolutional network has a convolution operator and filters, which basically convolves on this input image, and in the process downsamples the image by something by using another operator called pooling, right? So you apply a filter on the image, convolve it with the image, and in the process you generate a smaller size image, right? So if you start with, for example, 1024 by 1024 image, and you apply the first level of fully convolutional network, you can downsample it to 51 by 512, and again you apply a series of such convolutional operators. It downsamples the image to all the way to 32 by 32. Okay. In addition to the convolution operator, we also use a linear rectifier activation function, which learns the nonlinearities of the input. Okay, so that is what encoder does. In the decoder part, it does exactly opposite of the encoder. It upsamples the layer by creating a filter which is larger than the downsample image, and it uses a operator called deconvolution, a transpose in convolution, which generates the bigger images. Okay, so these two operations are done in such a way that the encoder part learns to identify the details in the images like edges and features of humans' faces and things like that. So it can segment the image nicely. Okay. The upsampling part basically learns the general characteristics of the image, like a high level segmentation part of the image. It can do. It can isolate the different parts of the image, like separating image, like if the image contains car as well as human, then it can learn to separate cars as well as image. But when it comes to the detecting as a human itself, like different parts of the human, like eyes, face, body, those detailed features are understood by the encoder. Okay. Now the encoders and decoders are connected with each other at every layer through something called as the skip connections. So these are the skip connections, right? And it is skip connection that is really creates the magic. So skip connections basically combines the output from the convolutions of the encoder, and it combines it with the downsampler's convolution layer. So it concatenates the two, and it does that for each and every convolutional layer, right? So what we do is we take the detailed characteristics which are coming from the encoder, and then we combine with general characteristics which are coming from the decoder, concatenates them together and feed it to the next layer. So in the process, the entire unit model learns to identify general as well as detailed features of the image, and then it can be trained in such a fashion that it can isolate different parts of the image, and it could also isolate the noise from the image. Okay. The unit model is called so because of the shape of the model. This encoder, this downsampler and upsampler, actually if you combine together, if you see, it creates this U shape model which resembles the letter U in English alphabet. That's why it's called the unit model. Okay, so externally if you take a look at it, what it does is it takes this noisy image as an input. Of course it goes through an encoder, generates the noisy image latents because the unit operates only on latents. Then the unit model learns to isolate this noise, which is denoted by these black dots on the image, and it predicts that noise in form of latents. Okay, so the latents are then decoded by the decoder, and this is actually the actual image of the noise, right? And then if you subtract this noise from this noisy image, what we get is basically the clean image. So that's how the unit model works. Let's also talk a little bit more about clip model. The job of the clip model is to generate an embeddings for a text as well as an image which are in the same embedding space. So here's an example. We have a text input called beautiful day in Hawaii. When it passes through the clip model, it generates a set of embeddings, right? Similarly, if you pass an image to the clip model, it can also generate the set of embeddings. So the output of the clip model remains same. It's always embeddings. Now in this case, this image still resembles the image of a beautiful day in Hawaii. So the embeddings that clip model generates in this particular case are very close to this embeddings because both of them semantically mean the same thing, right? So internally the way it works is when we train the clip model, we supply the model two inputs. We supply a set of images and a set of associated prompts. Like for example, here the top level image is an image of a puppy, and we are giving a text as Peppa the Aussie pup. Okay, so we basically generate this set of pairs of image and text, pass it through image encoder, and compute the dot product of each of this pair. Okay, the Cartesian dot product. So as you can see, the T1 here represents the text for this paper, the Aussie Pup, and I1 represents the uh, image of this particular dog. Similarly, T2 represents the another set, and I2 represents another set. So T1, I1 basically they are correlated to each other. Similarly, T2, I2. Then we compute the dot product of all of them, and we train the model in such a way that it maximizes the dot product of these two, all the diagonal elements, because there the text and image are basically close to each other, they are semantically same, right? So here it maximizes this particular dot product, and that it minimizes at the same time these other ones which are not at all related, right? So we take an image text pair as an input, and it maximizes the dot product of related image text pairs, and it minimizes the dot product of other image and text which are unrelated. And in the process, it learns to generate the embeddings which are in the similar space. The next part of the diffusion model is the variational autoencoder, and we have talked several times about this. The variational encoder model consists of two components, encoder and a decoder. The job of the encoder is to convert an input image to a lower dimensional representation called latents, and the job of the decoder is to convert latents back to the original image, right? And we do this because lower dimensional input are much faster to compute, and that is what is being fed as input to the unit model. The job of the noise scheduler that we saw in the model earlier is to add a different level of noise at the different time intervals and feed it to the model. For the same image, it can generate a different amount of noise and add it to the image at different time intervals, and this helps the model to learn to isolate the different set of style of noise from the image, and in the process it makes the model more robust to learn and create a clean image from the training image. So in the next model, we will actually go through how you train the diffusion model with and without text, and how it learns to infer or generate the image from the noise as well as image as well as text input.